Hi everyone, my name is Sean Taylor. I work for Bill Scalia, and today I'm sitting down with him for an explanation on his development of physics involving light and heat particles. I won't take up too much of his time. Here is Bill Scalia, the owner of his patented LED upgrade solutions.
Thanks, Sean. So what we're going to be talking about today is how dark matter facilitates light and how a dynamic crystalline structure of the nucleus of a molecule facilitates heat conduction. And the reason we're doing this is we're trying to understand how LEDs work and how they can produce light and heat. When you put electricity into an LED, it makes a percentage of heat and a percentage of light, and we're trying to understand how to affect those percentages. So the current description of the LED talks about it being a p-n junction and giving off photons of light, but there's no real good way of determining what percentage of light you'll get and what percentage of heat you'll get. So to begin with, Scalia Physics is based on two fundamental particles, the electron, which we all know, and the newly proposed inertiatron, which is a coin-shaped particle, and it's got a magnetic field on one side and a positive electric field on the other side. So all physical, chemical, and electromagnetic reactions can be modeled with these two fundamental particles. So 1836 of the inertiatrons form a proton, and they make an outer shell of the proton basically has an outer shell, which is the inertiatrons, and the magnetic field faces in and dissipates at the center, and the positive electric field faces out. So if an electron and a proton collide at a high enough speed, the electron can move to the center, the coins on the outside of the proton flip, and the electric side faces inward to cancel out the electron, and the magnetic side faces outside, and it creates a neutron. So basically, when the universe was first created, there was a uniform distribution of inertiatrons and electrons, and as the inertiatrons combined to form particles, the distance of separation between the particles increased because there are fewer particles in the same amount of space. So at some point, the inertiatrons reached a distance of separation where they could no longer react with each other. And this is what dark matter is. Dark matter is a uniform distribution of inertiatrons throughout the universe that are far enough apart where they cannot react with each other readily. So what's interesting is the uniform distribution of inertiatrons can be acted upon and transformed into an electromagnetic wave, and this is how electromagnetic waves propagate through space. We'll go into this in a little bit more detail, but basically a uniform distribution of inertiatrons, the dark matter is what we would call inertia, and the electromagnetic wave is what we call energy. So the inertia of the uniform distribution can be converted into the energy using the equation E equals mc squared. So we're all familiar with jets making sonic booms when they pass through the air and break the speed of sound. They actually disturb the air molecules and create a pressure wave that moves away from the airplane, and we hear a sonic sound. So what I'm proposing is that when an electron breaks the speed of light, it disturbs the dark matter or the uniform distribution of inertiatrons and creates a light boom, which would be electromagnetic waves that propagate out away from the source of the electron. So once again, we go back, so we can say that light is formed when an electron breaks the speed of sound and interrupts the uniform distribution of the inertiatrons to create an electromagnetic wave that propagates throughout space. And once the wave passes, then the inertiatrons go back to their uniform distribution because of the makeup of the field. So now that we understand how light is made, we need to understand how heat propagates from one molecule to the other. And I've come up with the concept of a dynamic crystalline structure. So the nucleus of an atom is a region in space in the shape of a sphere, in which the protons and neutrons reside and orbit in defined ways. The protons and neutrons in the nucleus of an atom spontaneously arrange themselves in dynamic crystalline structures. These dynamic crystalline structures dictate the properties of the atom and how heat propagates. So as we study this, the first atom we'll look at is hydrogen, which is just one proton and one electron. The proton resides in the nucleus and the electron orbits outside of it. The next one would be helium, which has two protons and two neutrons, and they're arranged in this structure you see on the screen, and the red protons can rotate in a horizontal axis, and the blue neutrons can rotate in a vertical axis, and they can absorb heat energy in the form of increased flywheel motion. So from this we can see that atoms and molecules absorb heat in the form of increased flywheel motion within the nucleus. In addition to that, we can see that the neutrons repel the electrons and the protons attract them, so the electrons are going to be in predictable regions around the nucleus of the atom. So the next molecule you would think would have 3 and 3, but it doesn't. It has 3 and 4, and this is how we can start to see how the characteristics of the atom are defined by the dynamic crystalline structure. This is lithium, and you can see that the four neutrons can orbit in the vertical axis, and the 2 outside protons can orbit in the horizontal axis, and the third proton is basically shielded by the neutrons. So what's going to happen here is 2 of the electrons are going to be tightly held, and 1 is going to be very loosely held, so it will be able to be pulled off of the atom very easily. So lithium is going to be a highly reactive material, while helium is going to be a neutral material. So this is how dynamic crystalline structure can affect the characteristics of the atoms. So the next one would have 4 and 4, but we see that would create a cube, and there is no way for rotation without changing the distance of separation between the protons and neutrons, so this would be unstable and would break apart. But if you add a 5th neutron, then you see we go back to our axes of rotation that can absorb heat in the form of flywheel motion, and now we see, since the neutron is in the middle, all the electrons will be more tightly held, and this is beryllium, and this is why beryllium would be less reactive than lithium and also be smaller. So the next one is boron, which actually has 6, and it winds up with this structure, which would have a more loosely held electron. And boron will be more reactive than beryllium. So now that we sort of understand this concept of dynamic crystalline structure, we can now understand that light is a disturbance of the uniform distribution of dark matter, and heat is increased flywheel motion in the nucleus of the atoms. And what we have here, when we look at magnetic and electrical things moving around, Faraday's law says that the faster they move, the greater the resistance to flow. And this is how we begin to explain how LEDs can change the percentage of light and heat that they produce. So basically, with this description of the LED, when the electrons are, when a voltage is applied to the LED, the electrons jump across the junction to the other side. As they jump across the junction, they break the speed of light and give off a light boom, which then disturbs the dark matter and becomes a propagating electromagnetic wave, which then dissipates throughout space. And when heat is created, then it's stored as increased flywheel motion of the material of the LED. Now that increased flywheel motion causes a greater EMF, or a resistance to electron flow, which then causes a percentage of the electrons to pass through as current but not break the speed of light because of the resistance to flow, so they do not make light. They pass through and create heat. So as we can see, the greater the temperature of the LED chip, the lower the amount of light that is produced and the higher amount of heat. So with this model, we can accurately mathematically determine what percentage of the electricity would be converted into light and heat based on the heat flow characteristics of the LED. So here we have a schematic of a typical LED where the chip is on top, and then you have a board, and the heat usually flows through the board and out to a heat sink. And on the right hand side, we can see the numbers for this, and we can see that the total thermal resistance of an FR4 type LED board would be 29 degrees per watt. And if you look at a metal core board, it would drop down to 0.21. So if we go to the design of our concept, we have heat that propagates out in a circular pattern away from the LED, and we can see that the thermal resistance is down in the 0.000001 range. So we're exponentially lower in our resistance to heat flow, so we can remove the heat from the LED faster than the LED can make it. So we're going to have less flywheel motion in the material that makes up the LED, and less thermal resistance, less electrical resistance, so a greater portion of the electricity will be converted into light. And since we're such a very low amount of thermal resistance and electrical resistance, then we can get a very, very high percentage of the electricity converted into light. So here is a thermal image of fluorescent lights and normal LEDs, and then our LED board in the middle. And purple is cold and orange is hot. So we can see that this is not just a theory. We can actually measure it and know that our LEDs are running at 1 or 2 degrees above ambient, while the other ones are running at 60 degrees above ambient. So basically, the light output of an LED is based on junction temperature. As the junction temperature goes up, the light output goes down. This is all in agreement with our new physics and description and model of LEDs.
Well, thank you very much, Bill, for giving us a good explanation here. Really, there's nothing out on the market like this. There's really no physics to explain it the way that you've explained it, and I really do believe that this kind of thing is going to change the way that we source energy and the way that we distribute it. And I'm excited for all of the benefits that this is going to bring. Already, Bill has put, it's over 1,000 lights?
Mm-hmm.
Over 1,000 lights in a military base, and over the past 5 years, they have had no complications, no issues. All they have is a glowing review. So, as well as the conservation, it also helps from people having a problem with the lights in the air, with the light being so well distributed. the distribution helps cover more area of the room. So it's not even a matter of how well it's using the energy, how well it's conserving costs, but really as a light, it's more effective. You have anything else you'd like to say, Bill?
Well, right now, I think that covers it.
Sweet. All right. Well, whenever Bill comes up with something new, we'll be back.
So can we listen?
Let's see. Where is the thing?
There's the record. Did we press record when we did that?
I pressed record. Oh,